Hello students, welcome to the third module of System Software and Compiler Design. In this module, you are going to learn some of the essential components of compiler and the first phase of compiler process called as lexical analysis. So these are the outlines of the content to be covered in the video. So we're going to begin with some of the essential language processes, and then you're going to see what is the structure of a compiler, what are the different phases it is comprised of, and then the evolution of programming languages, and then how it has influenced the compiler technology, the science of building a compiler. So what is the science involved in building a compiler? What are the applications of this compiler technology in the other domains? And some of the programming language basics which are required in order to learn the compilation process. Now, the second phase of the module deals with the first component of compilation process. We call it as a lexical analyzer. You're going to learn about what is the role of lexical analyzer, one of the important technique wherein the speed up can be done in reading the content of the source program, that is called as input buffering. And then you're going to learn how mathematical model can be used in order to specify and then recognize the tokens. The Lex tool, using which how the lexical analyzer can be generated of your choice, and some useful information about the finite automata. To begin with the language processes. So you all have used different programming languages and you have written different programs. And after writing the programs, you would be calling the compiler to execute it, right? So basically what you do, you write a source program, you call it a compiler. Compiler generates the target program, and to this target program, you supply the input and then you try to get the output. So essentially, compiler is one such tool. It acts as the translator, which converts the source program written in high level form to the form that the machine can understand. And the second type of executing your program is using interpreter. One of the major difference between interpreter and then the compiler is that here in interpreter, it does work one line at a time. So you're trying to execute a line along with providing the input and at the same time as an output. So you're going to get the desired thing. So examples for compilers, there are plenty: C compiler, C++ compiler. And then for interpreters, yes, we do have several example, Python. Then one more type of compiler here, we call it as a hybrid compiler. So wherein the compiler is designed in two steps, wherein initially source program is fed to the translator. It results in the generation of an intermediate program. And this intermediate program along with the input is then given to the next component. We call it as a virtual machine, and which gets the desired output. Our Java compiler is basically designed using the hybrid compiler. Now, the next question is it only compiler that is required to translate the high level program to machine level form? No, there are additional processors involved in this entire translation process, starting with the preprocessor. So the source program to be compiled will be given to the preprocessor. It does some preprocessing task. It will look for some preprocessing directive used in the program, and it will expand those lines wherever these statements have been made use of. For example, hash define and all. And this expanded or modified source program, it is then given to the compiler. And this compiler, it results in the generation of the target assembly program. And since the target assembly program is in the assembly level form, then the next component would be called here, it is the assembler. So assembler does the translation and it results in relocatable machine code. And this relocatable machine code, it is then given to the linker. So this linker is essential. Why? Because if your execution of the program involves linking more than one files, then this can be essentially be achieved using the linker. And this linker along with the loader. So this loader is very, very important. Why? Because after all the program has been converted, in order to make it execute, it should be loaded into the memory. So loading the object code into the memory, it is basically done by the loader. So essentially, all these components are termed as the language processors. So preprocessor, assembler, linkers, and loaders, sometimes they're also termed as cousins of compiler. Okay. Now let's move on to the structure of a compiler. The entire compilation process is divided into some 7 phases, starting from the source program. The source program, which we call it as a series of characters, it is given to the first phase. We call it as the lexical analyzer, and the lexical analyzer is also called as a scanner. It does the scanning of the entire source program, and it is going to divide it into some meaningful units called as lexeme, and for each of these lexemes it is going to generate what are called as tokens. Essentially, the lexical analyzer has to maintain the description of the patterns in terms of regular expressions. So whatever tokens that has been generated, so it is then given to the next phase, which you call it as a syntax analyzer. Syntax analyzer is also termed as a parser. It is going to check out whether the syntax of the token stream, is it correct or not, or in other words, a syntax can be formed or not. So how exactly it can be done? It is by constructing an appropriate syntax tree. So the syntax tree is also termed as a parse tree. So the construction may happen from top to bottom, or it may happen from bottom to top. So this syntax tree, it is then given to the next phase. We call it as a semantic analyzer. It essentially is going to check out whether the semantic of the syntax tree, is it correct or not. Or in other words, if at all the program makes use of some of the type checked variables and inappropriate usage of the constructs, so the meaningfulness of those statements, it will be essentially checked at the semantic analyzer. So the type checking and type conversion basically is done by the semantic analyzer. So the output of the semantic analyzer will be the modified syntax tree. So all these phases, lexical analyzer, syntax analyzer, and then semantic analyzer, so together termed as the front end of the compiler, or they're also called as analysis phase of the compiler. And the later phases, they are termed as the synthesis part of the compiler. They're also termed as the back end of the compiler. Okay. Whatever syntax tree that has been generated after the analysis process is then given to the intermediate code generator. Now this phase is responsible for generating the first step towards generating the target code, wherein it tries to generate some machine language statements using some sort of representation. And one such representation we will be using here, it is called as a 3-address code. Why the term is 3-address code? Because every statement it supports at the max using only 3 operands. And whatever intermediate representation form obtained after intermediate code generator, it is then given to the code optimizer, and this code optimizer, it looks for whether any optimization can be done to the intermediate represented code or not. Optimization in the sense whether the number of lines of code can be reduced, or the usage of the variables can be reduced, and then so on. So the modified or shortened intermediate representation will be the output after the code optimizer. It is then given to the code generator, and it is this code generator actually responsible for generating the target machine code. After generating the target machine code, an additional code optimizer can be used over here in order to fine tune the target machine code that has been generated. So these constitute the entire compilation process. Now let us consider one simple example, and we will see so how exactly the translation takes place. Now let me consider a simple example. Say you have a statement A equal to B plus C. This is one of the statement found in your program. And remember, so throughout the explanation, we are sticking to C programming language. And here we assume that A, B, C are the real variables. Now what happens over here? Now this statement is then given to the first component. So which is the first component over here? It is nothing but our lexical analysis. Correct. So the component to be used here in this case is lexical analysis process, or it is also called as scanning. So it scans through the entire source statement and then it just tries to check out so how exactly this statement can be divided into meaningful units. So here it is going to divide it into A as one meaningful unit followed by equal, then B, then plus, and then C. So the output after the lexical analysis phase is nothing but the series of tokens. So in this example, if I assume that the tokens to be generated for A, B, C are nothing but the identifier. So here it will be generated as ID is the token generated for A. Along with the token, an attribute can also be associated. So in this example, since A, B, and then C, they all represent the same token. So I will be using one identifier just to differentiate that there are A, B, and then C respectively. Okay. And then we have equal to. So what is equal to? Actually, it is an operator. So you can write it as OP or you can just write the equal operator symbol itself as a token. And then we have B. So what will be the corresponding token being generated here? It is nothing but identifier. And since it is the second identifier, so it is given a number 2. And then followed by the operator plus, correct? And then what do we have? We have the next identifier, that is ID, comma 3. Now this representation is called as a token string. Now what happens after the token stream? It will be given to the next component. Which is the next component over here? It is the syntax analysis. Correct. So we have syntax analysis. So what is the other name for syntax analysis? It is also called as parsing. So here it is essentially going to check the syntax and then this can be represented using the syntax tree. Okay. So here in this example, the syntax tree can be constructed in this way. Now, this particular expression deals with evaluating some expression, right? So you're adding B and then C and the answer is assigned to A. Correct. Now, the first step involved here it is to perform adding B and then C. So B is nothing but corresponding to token representation ID2, C corresponding to ID, comma 3. Fine. So we do have here ID, comma 2. Fine. And then what do we have? We do have ID, comma 3. Correct. So what should be done for ID2 and then ID3? So we need to perform addition. Correct. So addition will be performed. This is how it is. Fine. Next, what we have to do? So whatever resultant is contained in this node, it should be assigned to which variable? A. Correct. How exactly we have represented A after lexical analysis as ID, comma 1. So we need to have what? ID and then 1. Fine. So what is the operation to be performed over here? Assigning. Correct. So we have assignment. Sorry, it is a single assignment operator. And then what do we do? This is the basic operation. Now this is the output obtained after the syntax analysis phase. Correct. Now what will be done in the next step? In the next step, this will be the input to the second phase. So what is the, sorry, this will be the input to the third phase. What is the third phase? Which we call it as the semantic analysis. So what semantic analysis is going to do now? It is going to check out whether the semantic of syntax tree formed, is it correct or not, right? Now here in this case, there is no much operations will be performed by the semantic analyzer because A, B, C, they are all assumed as the real variables and nothing much type conversion is required. Okay, so the output after the semantic analyzer, so it will be the same as above. Next, what do we do? So Whatever output generated after semantic analysis, it is then given to the next component. Which is the next component? Intermediate code generator, correct? So we do have the intermediate code generator. So what intermediate code generator does? It tries to generate the machine language statements, wherein the representation used here, it is called as a 3-address code. Fine. So in 3-address code, the representation, it makes use of some of the temporary names. So here the statement would be written in this way. Okay. So initially you are going to perform ID2 plus ID3, correct? So this can be written as T1 equal to ID2, fine. And next, maybe essentially you're going to perform T2 equal to T1 plus ID3, addition takes place. And the next step would be assigning ID1, the answer contained in T2. If I assume that this is how the code that has been generated, correct? Now this will be the output of intermediate code generator. So after this, what happens? The next step would be to optimize whatever intermediate code that has been generated, correct? So this is then given to the which component? It is then given to code optimizer. Now in this example, so the code optimizer, it tries to optimize the code. So how the optimization will be in this case? Let us see. So instead of making use of unnecessary temporary variables, it can be used in this way, right? So you can have written T1 equal to, directly you can write the statement ID2 plus ID3, fine. And then you can assign ID1 the value of T1. Okay. And here ID2, ID3 represent the memory location. We cannot have memory equal to memory plus memory. Okay, so that is one of the general rule we'll be following. So accordingly, you can have ID2 plus ID3 being assigned to some temporary names T1. And from this T1, the value is assigned to another memory location ID1. Okay. And next, so what happens after code optimizer? So this will be given to the next component. What is the next component? The next component is nothing but our code generator. Fine. So what this code generator is going to do? It is going to generate the target code. If I assume that the target code to be generated here in this case is some assembly language statements, and here it has to follow some of the instructions of the supported computer architecture. Okay, so here I can write it in this way. So the operation to be performed is adding and then assigning the value to the final memory location. Okay, so you can perform the operation in this way. So you can perform load the value of, so what is the appropriate instruction you can use? Load F. I'll be making use of F just to represent that the type of values I'm dealing with here, it is a floating point value or nothing but the real values. So you have some register, let me call it a register 1, okay, and to which you're trying to load the value ID 2. Okay, and next what you can do over here, you can perform addition. So what is the addition operation? ADDF, right? Maybe I would be performing the addition of R1. So before performing addition R1, okay, so maybe I can try to load the content of ID3 into R2. Okay, and then what you can do, you can perform add, right? So you're trying to perform the addition of R1 and then R2, and then essentially you're trying to store the resultant into R1 back. Okay, and then the resultant is in R1, so it must be stored back into where? It must be stored into ID1 from R1. Okay, now this is the code generator, and then here, assuming that there are nothing much optimization can be done, so we can restrict the number of phases to only 6 phases. Okay, now let us consider one more case. Okay, fine. Let me consider the next case, wherein considering the assignment statement position equal to initial plus rate into 60, and where all the variables are real, then the translation of this statement is shown in the following diagram. We begin with the lexical analyzer, and then we have lexical analyzer resulting in the generation of the token stream ID1, ID2, ID3, and then 60, and then passed on to syntax analyzer. And in syntax analyzer results in the generation of the syntax tree. How is the syntax tree constructed? Initially, you need to perform rate into 60, correct? So rate is represented using the token ID3. You're performing ID3 into 60, and this answer gets added with ID2, and this answer is then stored into ID1. Okay. Now, this is the syntax tree being constructed. It is then given to the semantic analyzer. So what semantic analyzer does over here, you can just check it over here. In the semantic analyzer, it just checks that 60 is written as integer, but whereas rate is a floating point variable. One of the common policy employed in any programming language is that, so the type compatibility. So here, essentially, the semantic analyzer, it tries to convert this 60 from its integer representation to float. Okay, so this resultant is then multiplied with ID3. The answer is then added with ID2, and the answer is then assigned to ID1. So one point you can note over here is that the usage of the operand, the left operand and then the right operand, the position are not supposed to be changed. Okay, because if you consider multiplication, its left operand is ID3. ID3 is nothing but rate itself. Its right operand is 60, correct, which is nothing but a numerical value. Fine. And similarly, if you consider operation plus, so with respect to plus, we have the left operand ID2, that is nothing but variable initial, and its right operand is nothing but the answer obtained after rate into 60. So this is how it goes. So this will be the output after semantic analyzer is then given to the intermediate code generator. Now along with these phases, here you can also see the usage of an additional data structure. We call it as a symbol table. So now the usage of the symbol table is also very important, because so whatever meaningful units are seen by the lexical analyzer, it has to maintain these details in one particular data structure, because these details are required in the upcoming processes. Okay, so here it maintains, you can assume that there is a table and it is made up of several number of rows, and each row corresponds to maintaining one such lexeme information. Along with the lexeme name, it can store some additional attribute information also. Here we are not dealing with any additional attribute values, so you can just assume that the symbol table is represented in this way. Okay, because these are required for the further processing. Okay, now the output generated after semantic analyzer is then given to the intermediate code generator. What it does, it initially convert 60 from integer to float assigned to some temporary variable t1, and then it does the multiplication of ID3 and then T1, which is assigned to T2, and then it does the addition of ID2 and then T2, which is assigned to T3, and from the temporary name T3, it is then assigned to ID1. And then this code is then handed over to code optimizer. What code optimizer does here, it does the multiplication of ID3 and then 60.0 straight away. Okay, so here itself the conversion is taking place and the resultant is stored into some temporary variable T1, and this T1 and then is added with ID2. The answer is stored back in ID1. And this is then given to the next component, which is the next component, code generator. So what code generator does here, it generates the machine language statement. Here in this case, we have assumed assembly language program as our target machine code. So you are loading ID3 into R2, and then you are trying to perform the multiplication of this ID3 with an immediate value 60.0. Answer is stored in R2 only, and then ID2 is then loaded into another register R1. Then you are trying to perform the addition of these floating point values R1 and then R2. The resultant is stored in R1, and then finally from this register R1, the value is stored into the memory location identified by ID1. Okay. With this idea, now there is a task for you. If you have a notebook along with you, or if you have any sheet, please write the translation of statement AB equal to CD plus EF minus GH into 50, where all the variables are real. Write the translation of C statement AB equal to CD plus EF minus GH into 50, where all the variables are real. Okay, so solve this particular problem. I'll move on to the next slide. So there are some components, some topics which you can do a self-study. The material is already shared with you. You can just have a look into it. So one is compiler construction tools. So ever since the invention of the compiler, it has resulted in the generation of various tools. The different tools came to the market, and then some of the tools such as parse generator, syntax directed generator, and then so on. And researchers were trying to make use of these tools in order to check out how effectively this can be used. And then the other learning component here would be the evolution of the programming languages. So which deals with uh, how exactly the languages were evolved, and what are the different ways these languages were classified, and how exactly these languages had influenced on the compilers. Okay, just 1 or 2 pages you can study by yourself. Okay. Now, let me touch upon what is the main science of building a compiler. So here throughout the compiler concept, you're going to look into compiler as one mathematical model. So the basic science behind the compiler is that, so you're taking a problem, right? Taking a problem is nothing but you want to learn what is a compiler is, right? Compiler is nothing but it has to translate a language written in one form to another form, right? So that would be a problem. And then you have to formulate a mathematical abstraction, and we have shown you the various phases. In every phase, so you're trying to make use of one sort of mathematical abstraction, and then you're trying to solve it using mathematical techniques. Okay, so these are the main steps used in building the compiler. So some of the mathematical models which are used in the compiler design are finite automata, regular expression, context-free grammars, and then trees. So finite automata and then regular expressions are used in the lexical analysis phase, whereas context-free grammars and then tree concepts, they can be used in the parsing step and then the semantic analysis phase. Next, the focus was mainly onto the code optimization. So the code optimization had its own objectives. So it was said that the optimized code, it must be very much correct, and it must improve the performance of many programs. The compilation time must be kept reasonable, and then the engineering effort required must be manageable. So these were the initial objectives which were set, and accordingly the compilers were fine-tuned, and then a lot of development had taken place, and much sophisticated compilers are available nowadays. Okay. Now, similarly, we have got one more learning to happen by yourself, self-study, applications of compiler technology. So some of the areas highlighted here are, so implementation of high-level programming languages, the optimization for computer architectures, so especially in the area of how parallelism can be achieved, and then the memory hierarchies, how effectively, so it can be used in the execution of the program. So they are all connected to one another. And then all these ideas gave rise to designing the new computer architecture also. And then how exactly the concept which is used in the compiler were tried to use for other sort of translation. Okay. And then other sort of translation, maybe the usage of the compiler technology, it is not only restricted to converting high level language to the machine level language. So any sort of translator you consider, maybe you consider any query languages or script languages, the translation mechanism employed in any of these tools, it is the same. And then some components of the software productivity tools. So they were much sophisticated, tools were developed due to the high development of the compilers. Many softwares were also developed. So all these are the applications of the compiler technology. Okay, now with this idea, so some of the little basics of the programming languages we need to know. So all these concepts are known to you, but still we will have a look into it, because these concepts essentially influence how a compiler has to be designed. So starting from the starting act, then the dynamic distinction. So here every programming language, it defines its own policies, especially the static and then the dynamic policies. So that is nothing but some policies which are defined during the compile time of a program, and some policies which are defined during the runtime of a program, especially with respect to the usage of the variables. Some variable, some construct, so their usage, their definition, everything has to be decided during the compile time, whereas some variables usage, it has to be decided during the runtime. Now with this, there is an additional component employed here is environment and then the state. So what do you mean by environment and then state? Because when the compilers were trying to evolve, and it had impacted whether whatever changes that has been taken place, does it actually influences the name of the variable, or does it really influences the value you're going to deal with? From the process of declaring any variable and by assigning to value, so there exists two level mapping, and this mapping is referred by environment and then state respectively. Okay, so you're going to make use of, say for example, int a equal to 20. Fine. So where in this case a is nothing but a name. For you it is a name, but actually for this name, internally, the machine has to allocate one particular location. Correct. So this is where we make them the term variable. Now there exists a mapping from name to its actual location, and this mapping is referred by the environment. Similarly, what is the value stored in this particular location, or what is the value assigned to this variable? There is another level of mapping. So this mapping is from location to the value. It is called as a state mapping. So there were little confusions on to, so how exactly this can be dealt with initially. So these were also being taken into consideration. Another programming language basic we need to learn here is the static scope and then the block structure. So block structure is nothing but a set of lines of statements which are enclosed within the flower braces, and it tells you what is the scope of a variable. In the sense, a variable can be defined anywhere else in the program, the same variable. What is the usage of the variable within that particular program? So that corresponds to its scope. For example, here in this example, I can say that, so we have a main function. So starting from the open brace and then close brace, all these statement belongs to one particular block. We call it as B1. Okay. And under B1, we have written the statement int A equal to 1, int B equal to 1. Fine. And several other statements. Now after int b equal to 1, we have another open brace, right? And the corresponding closing brace can be over here. Now whichever statement that comes between these braces, it belongs to another block. We call it as B2. So under B2 block, we have declared another statement, int b equal to 2. And then we do see the usage of open brace and then the closed brace. So there are some statements, and these statement belongs to block B3. Similarly, under the same block B2, there is one more pair of open and then the closed bracket. So wherein we see the usage of statement B equal to 4 and then C out A and then B. So here it belongs to another block called as B4. Here essentially the program is nothing but C++ program because it makes use of the C out statement. Okay. Now, what is the scope of the declaration? We will see starting from int a equal to 1. Correct? So what is the scope of int a equal to 1? To see the scope of a equal to 1, we just see the usage of the same variable where in other places it might have been used. The usage of a equal to 1, of course, it must be entirely within the block B1, correct? Except for block B3. Why except for block B3? Because in block 3, the same variable a is defined using another value. Correct? So within block B3, the scope of A equal to 3 will be taken into consideration, even though A has been declared and defined as equal to 1 in block B1. So we say that the scope of the statement int A equal to 1, it is B1 except for B3. Correct? So you can see the scope of variable int A equal to 3. What is the scope of variable int A equal to 3? It is only within block B3, correct? So what is the scope of the statement int B equal to 4? It is only within B4, correct? Next, if we see the scope of variable int B equal to 1. So what is the scope? So the scope of variable B equal to 1, it is entirely in block B1 except for in B2. Why except for in B2? Because in B2, B is redeclared and then redefined. Got it? And similarly, if we see the usage of int b equal to 2, what about int b equal to 2? So the scope of this b equal to 2 is entirely within B2 except for B4. Why? In B4, it has been redeclared and then redefined. Okay. So now every programming language, it has its own policies. Accordingly, the compiler has to work. Okay, there are several other features also should be taken into consideration is explicit access controls. We have learned the concept of class, structure, and several other operators whereby you can have the accessing of the members and all, right? And then the dynamic scope. Dynamic scope refers to the usage of the variables which is dynamic in nature. Simple example here is the usage of macro expansion in C. So you have a macro called as A, right? So it should be expanded into x plus 1, correct? So you have a statement x equal to 2 and two functions have been defined, b and then c. And within b, you have initialized x equal to 1 and then you're printing the value of a. And then within c, you're just printing the value of a. And then you are calling the main function by calling b and then c respectively, correct? Your program executes from main function and then you're calling b, the control goes to b, and here it takes the value of this x because the scope of x equal to 1 is within b, correct? X equal to 1 and then you're printing the value of a. But what is a? A equal to x plus 1. But what is x? X equal to 1. So what will be printed over here? It is 1 plus 1 equal to 2, correct? Next, the next statement to be executed here, it is C. So what about C over here? You're just printing the value of A. So what is the value of A over here? So here A equal to X plus 1. Now what is the value of X being taken into consideration over here? It is nothing but X equal to 2. Why? Because X is declared globally. The usage of the variable X is in this entire block, correct? So the answer here it would be for the second printf would be 3. Fine. And similarly other concepts you have, that is a parameter passing mechanism, call by value and then call by reference. So all these points must be taken into consideration. Okay, so I will stop the first phase of the module 3 over here, and the second phase of the module will be covered in the next video. Thank you.